Okay, sorry about this delayed start. So we had this thing in our lab class, and we wrote part of the code. In today's class, I would go for some of the operations so that we can make it a real calculator, sort of. And I was looking at the code that we have. So here I left you a homework that you have to treat 0 in a different way. Did you guys manage to do this? Yes? Okay. All right, that's good. And no one else? That's going to be a problem. We need to learn how to use the Java documentation. Well, let me do this one for you, but I mean, you guys need to work with the stuff that you're assigned for exam preparation as well. One thing I want you to notice, I went through this before, but let me just talk about it first. See, we can repeat these things, like if we click on a particular button, it appears multiple times, that text. The problem with 0 though is that the leading zeros, they don't make sense. So if you type in a number like 00012, that really doesn't make sense. It should be just 12, right? If you have trailing zeros, if you have zeros afterwards, that's not a problem. It's just that the zeros that are on the left side, they don't make sense, so why put them in the first place? Okay. One single 0, that's all right, but if you have 0, 1, then again, that's not something you'd want to put in. So first of all, how do we fix this thing? You see, the problem starts right over here. So if you have a single 0, maybe the user really wanted to put a 0 in. That's what the number is, and that's fine. Now, if you put a non-zero number afterwards, what should you do? Remove the first 0. Okay, so that's one thing. If you put a second 0, what should you do? Remove the first 0 and leave the second 0, or do you remove all the zeros altogether? If you remove all the zeros, then it's again a problem, because there should be a single 0 if the user really wanted to keep 0 in there. Okay, so it really boils down to one thing here. If you have a 0, and then if you start typing anything, whatever number it is, you're going to take that 0 off. Okay. So, see what we do? We do our new value equal to old value plus 0. Okay. Now, I'm not opposed to that. It's just that we're going to write it in a slightly different way. So we have a string new value declared, and this is where we need to write an if-else statement. If our old value either starts with a 0 or the character at position that holds a 0, then we do something like this. We can say starts with. If this is starting with 0, then the new value is going to be just a single 0. If it is already 0, it's going to be a single 0. Otherwise, new value equal to old value plus new value. Oh, not new value. Plus 0. So, how does that work? Let us just try it out very quickly. So previously we could type in a lot of zeros. Now we can type in a single 0. But if I tap multiple times, it doesn't work. I can type in 1, 2 like this, and well, see, now is another problem. as soon as we type 0, what happens? That goes away because of what? Because it started with a 0. I mean, it is not a problem if you have a number that's different. Let's say 1, 2, 2, 2. If you have a lot of zeros afterwards, then it's fine. It's just that somehow, if you have a 0 over here and you press a 0, then everything goes away. Okay? But this thing, if I type in 1 or 2 after a 0, it's not working properly. We don't get that 0 removed, which is what we really want. What to do then? Well, we have to change the code for the other ones as well. Just as we did this for 0, we have to do the same thing for 1 and 2 as well. This was for 2, so we put 2 in here, and this one was for 1, so we replace that with 1. So with that change, now, I mean, we can type in numbers like this, which is not a problem. But if we have multiple zeros or a single 0, I mean, if you press whatever many times you press 0, it's not going to be a problem. See, that 0 was taken out now. We had a 0, but it's gone. But trailing zeros are all right. So we had to change the code for each and every one of these things. And if you have 9 other non-zero digits, you have to change the code in 9 different places. Okay. This is a solution, but not really an ideal solution. It's just that the effect of change for a simple thing means that you have to change a lot of things. This is something we will modify later on when we get to know about polymorphism. Okay. So let us now imagine that we got all these numbers, all these digits coded in. We have all these buttons, and they work properly, which it's not the case in our scenario. Like, we don't have code for, we don't even have label for these things. So really, let us at least put those in, because that's not going to take time. This is 5, 6, 7, 8, and 9. So at this stage, well, we don't really have code for anything other than 0, 1, and 2. Okay, that's our limitation, but it's really not a big deal. You can copy paste the code and make some small changes to get the code for the other buttons, like 3, 4, 5, 6, 7, 8, 9. You can do that. Let us talk about these options. This is addition. Here we may have subtraction and the other operations as well. So in order to get them to work, we need to devise how this entire calculator is going to function. And in that respect, I want you guys to realize that it's actually difficult to process the way we do things. So if you look at the calculator that's provided to us over here, it works pretty good. So if you're given expressions like 2 plus 3 into 4, what should be the result? 14 or 20 or 9. Which one is it?
9.
How is it 9? 2 plus 3 into 4. I mean, the options that I can probably think of is either 20 or 14. There are two different ways to look at it. Yes, the answer is going to be 14. Why 14? Because multiplication has higher, what's this called? Precedence. Multiplication has higher precedence than addition. That's why this happens first. 3 times 4 is 12. 12 plus 2, that's 14. Okay, so this is how we do things. if it were a slightly more complicated expression, right, 2 plus 3 into 4 divided by 2, or let us make things a bit more interesting, 3 into 5 divided by 2 plus 1 minus 2, and let's say plus 3. What would be the order of operations? And just to make sure that we get different results, let us say that we only work with integer arithmetic. This is to say, if you have 5 divided by 2, the answer is going to be 2. It's not going to be 2 by 5. And our computers, they work in that way as well. I mean, if you don't trust me, I mean, this is easy to show. Just let us declare two variables, int x equal to 5, int y equal to 2. Let us just declare another double variable, z equal to x divided by y. So you can actually hold floating point answers, right? So if I print this result, let's just quickly test this out. The result is actually 2.0. So as you can see, if you divide 5 by 2, you get 2, not 2.5. That's because integer arithmetic, they work faster, and that's why when the compiler sees that I got two integers, why am I supposed to do a floating point division? Let's not bother about it. Let's just do integer arithmetic. That's why we get 2 as a result. So it's really going to be a different thing. So the expression that we got here, and let me copy this over. I need a journal. And what we got? We got this. So this is what we are trying to solve. Okay, and let us do this step by step. What would be the first operation that you'd perform here? Multiplication or division? Right. Let's see hands then. How many of you are saying division? And how many of you are saying multiplication? All right, that's me as well. Okay, so yeah, I don't blame you guys. Really, I don't blame you if you say division first, because we were taught to memorize this thing. And if you're working with computers, we don't consider that anymore. Okay, this is gone. Let me cross it off in a better way. That's bad. Okay, what we deal with instead are two things. We talk about precedence, and there's another very important terminology. What's that goes along with precedence? Precedence and associativity. As computer science students, you guys need to know about these terms and what they really mean, and how this affects the entire calculation. So when we talk about precedence, we talk about the relative ordering of these operators. We have multiplication and division, and also the modular operation, modulus operation. These three operations, they have higher precedence. So let me go with ordering. So in the first order, we have multiplication, division, and modulus. These operations, they are at level 1. Okay. Second comes addition and subtraction. But in terms of multiplication, division, and modulus, we don't have any precedence at all. They are at the same level. So how do you decide which one will happen first? Multiplication or division or modulus operation? You decide based on associativity, and this one will say whether your operator is left associative or right associative. Okay, there are two different things. Well, actually, these are not orders, so let's not write 1 and 2. So we have left and right. And over here, I purposefully skipped one thing, that's the parenthesis. Parenthesis has higher precedence than any of these things. I left that out. See, associativity says that if you have operators of the same precedence, then you, depending on the operator type, you go either from left to right or from right to left. It really depends. So let me give you a quick example of this, and probably that would make sense. What's the answer over here? What does it evaluate to? 2 to the power 3 to the power 2 is equal to what? 2 to the power 6. Is that it? Or is it 2 to the power 9? Or is it 8 to the power 2? See, whenever you have powers, all right, let us forget about 2. If you had 3 to the power 2, it's not going to be 6, it's going to be 3 squared, and that's 9. So the question is really either you consider this to be 2 to the power 9, or you consider this to be 2 cubed is already 8, and square that. So which happens first? And in school, in primary school, I think we learned how to deal with these things. If it is about exponents, if it's about powers, you go down this way. So you calculate 3 squared first, and then you do this. You don't really use brackets to say this, but you have to come from top downwards. So 3 squared, that's 9, and 2 to the power 9, that's 512. And that's going to be the answer. It's not going to be 64, it's going to be 512. Okay. Why am I talking about this? Because we got powers. So if I write this one as flattened out in this fashion, this is a good example of right associativity. You do this one first, the rightmost one first, then do this one. This is right associative. Whereas if you have, let's say 2 into 5 divided by 2, yes, I know in primary school we were also taught this, that do the division first. And if you try to do that on computer, you get 5 divided by 2 is how much? 2 times 2, that's 4. So 4 is one possible answer. However, we are not going to go that way. For division and multiplication, they are of the same precedence, and that's where these operators, they follow the left associative rule. So in terms of left associative rules, what do? You do 2 times 5, that's 10. 10 divided by 2 gives you 5. 5 is not equal to 4. We get different results. Okay. And that's why this thing really matters. You need to understand how we deal with these things in terms of associativity and precedence. Right? Precedence comes first. Then if you have any ambiguity, if you're stuck in a decision, you have to pick the right associativity for your operator. If it is multiplication, division, and modulus, or addition and subtraction, then you always go with left associativity. If it is about exponents, like that, you go with right associativity. Is that clear? And just to make this really crystal clear, and I'll give you a very simple example of associativity. let's say we got 2 minus 3 plus 4. A very simple example, right? This is two operations. We got a subtraction, we got an addition right here. They're of the same precedence. Addition and subtraction, they're of the same precedence. Okay? So you need to know. Just a minute. Hello? Asif? How's it doing? So what I'm saying here, we got subtraction and addition. They're at the same level. They're the same precedence. But we talked about associativity, and they're left associative. Okay, left associative means that you do the left one first. Sorry about that. Okay, so we got a left associative. If we consider left associative, see what you get. You do the subtraction first. So 2 minus 3, you get what? Minus 1. And then you do the plus thing. And that's what? 3. Okay, so we can do the left associative one as minus 1 plus 4, which is equal to 3. Or we could also do it differently if we were following 2 minus 3 plus 4 as right associative. Then we do 2 minus 3 plus 4 is equal to 7, which gives you minus 5. So you can see that based on associativity, the way you do your calculation may end up giving you the right answer or the wrong answer. Okay. So, I mean, this is easy to understand with the addition and subtraction, perhaps, that this really makes a difference. And these are, by definition, these are left associative work. And the same thing goes for multiplication, division, and modulus. So from now on, for us at least, we're not going to follow this Bodmer's rule anymore. If you're talking about multiplication and division, if they're at the same level, you do whichever comes on the left side first. So if you got this expression, right, if you want to evaluate this, what is the first thing that you're going to do? Asking the same question again. You do the multiplication, you do this multiplication first, right? And that gives you 15, and then we have a division. So let us do this step by step, although we have done that a lot of times in probably class 5 or class 6, something like around that time. We have done plenty of math problems, we have solved them. So we do 2 plus 15 divided by, where's my, yeah, right. 15 divided by 2, then plus 1, minus 2, plus 3. So what's next? 7 plus 1, minus 2, plus 3. And that gives us how much? Which one to do next? These are all of the same level, right? And we apply the left associative rule, so the leftmost one we'll take care of. We take care of that first. That's 9 plus 1 minus 2 plus 3. Okay? And then we do 10 minus 2 plus 3, and also 8 plus 3, and then again 11. This is how we solve these things. And those were probably difficult problems to solve at that point in time in our life, because we had to search for which one to do first. This one? No, because we got a subtraction and a addition over here, and both of them are of the same precedence, and they are also left associated. So do the left one first. I mean, this I showed you as an example, as a bad example actually. This is wrong. This is not supposed to be the way you work. You do it this way. You do things in a left associative way. Do this one first, and after that, do this one. Okay, that's the order of operation. Okay, so we know how to get to 11, right? But that's through some work. Like you have to find out in this expression which one to do first. And as I have shown you, well, not really. I haven't completed this. So if I hit enter now, we get the answer. We get 11.5 because this calculator is generous enough to keep the decimal point, like the floating point numbers are here. We get the right results. We got 11, and over there we got 11.5. No big deal. I mean, we could have gotten 11.5 right away if we had 7.5 here. So this calculator knows how to deal with these sort of things. Okay, but if you want to write a program that actually takes care of this, it's not an easy task. It wasn't easy for us back then, and it's not easy to do on a computer as well. We definitely can write programs like this, but in order to do so, we have to do one of two things. One could be that we write this as a tree and then solve that recursively. See, we are given this expression. I'm going to waste some time behind it, but this is an important thing to understand for us computer scientists at least. You see, when we have an expression like this, what we do is we find out the operation that happens right at the end, okay, which is going to be our plus operation that happens right at the end, okay, and then you branch out. That's going to be the root. Or in an easier way, if I am trying to explain this thing, I think it's easier to understand. This operation happens first, right? 3 into 5. So we write them down right at the bottom. So I'm going to build this tree bottom up. We got 3 and 5. And then what do? We do the division, right? We do the division. So let me try to draw this operator. And divide by what? Divide by 2. After that, what do? What do we add? We add 2. Then what do? We add 1. And afterwards, what do? We do minus 2 first. And finally, plus 3. Is this thing clear in this tree? So if you're given this tree, you know that the root is up here. That's an addition. And you can actually calculate the entire value of this expression just by evaluating this tree. How do you evaluate a tree? I mean, you have to bring the results bottom up, right to the top. So 5 into 3, that's 15. 15 divided by 2, that's 7. And 2 plus 7, that's 9. 9 plus 1 is 10. 10 minus 2, that's 8. 8 plus 3, that's 11. Okay. you can have branches over here as well. And this is a tree. So you calculate the results and you push them upwards to get the final output. So what's the real challenge? The real challenge is building this tree. How does the calculator work, or how does our program work? Because we can write an expression like this. We can say integer x equal to this whole thing, right? And we'd get 11 in there. Okay. Just to show you, let's say I just purposefully do that, not just that bit, the entire one. If I copy this expression and put it here, I have to change a few symbols, right? They're not here, like this one, or the multiplication itself. I have to change the operators, something like that. And then we can print the result of x. If I wanted to do this, we will get 11. Okay? Yeah, we got 11. So what's my point? I mean, this calculator, as well as our programming language Java, they both know how to deal with these things. Okay? Internally, the compiler knows how to handle an expression like this to produce the correct answer. And we should do that too. I mean, we should know how to do this thing. This is usually covered in data structure course and sometimes also in discrete mathematics course. So perhaps you have heard about this thing already. The way we have written this expression, this entire expression, from here down all the way down here, this is written in a particular format. This is known as infix expression. Have you heard about this term, infix? Nobody? Let me write the name of its cousins. We got infix, prefix, postfix. Does that ring any bell? Postfix and prefix, it does, but not for infix? No. Okay, so if you have the binary operators in between the operands, that's infix. If you have the operator beforehand, that's prefix. If you have it afterwards, that's postfix. That's in layman's term to understand things. See, what we do here, we get a tree like this somehow. I'm not saying exactly how, but somehow let us say that we are given this tree. Okay, magically somehow, right? Once we get that, we can generate both the prefix expression and postfix expressions. How many of you have done data structures already? Okay, well, some of you in the when we study stacks, usually that's covered at that time, the prefix and postfix stuff. So if you start over here, in terms of postfix, we have to go as deep as possible, then we crack back and we go again. So we're going to follow a very simple rule. Go left, go right, and then print once you're done. Okay? So we're going to follow this strategy. Let me just give a sense of direction, that do this one first, then do this, and then finally print this. So let us try to follow this thing. I know I'm wasting some time, but maybe it's not going to be wasted at all. I don't know. So can we go left from here? Can we go further left? Can we go further? Can we go further left? No, it ends here. So there is no left from here. Can we go right? No. So there is no left, there is no right. So at that point, what do? We print. So what do we have? We got 2. Okay? So let us go back. We are done with this. So we are back here. Can we go right? Because the left part is done. Can we go right? Yes, we can. And once you're here at a new node or entry point, what do again? We try to go left. Because every time, this is going to be the same thing we're trying to follow. Try to go left, try to go right, and then print. So we can go left, can't we? Yes, we can. So we go here. And can we go further left? Yes, we can. We can go left here. No. We can go right. No. We can go back. So you print. So what do we print? You print 3. And then you go back here only to come down again. And now what do we do? Try left, try right, and come back, and then that's when you print. So what do you print? You only print 5. Okay? So at this point, we're also done with 5. So we're back here. And if you look at this multiplication, we have taken care of both the left side and the right side. This is all taken care of. So we're done here, and that's why we print the multiplication. Okay, so the multiplication comes here, and then we're back to the division part, but we haven't went right. So you go right, try the left, try the right. Nothing's there, so you go back, so you print 2. Okay, and then when you're back here, what do? We have taken care of both left and right, so we write the division, and we go back here where we have also covered both the left side and the right side, and now we have what? Plus. And then we are up here where we see that there is also a right side to it, which we haven't visited. So you go left, we go right, and now we are back. What do we get? 1. And after that, plus, because both the left and the right have been taken care of. So you got a plus. And now we got some options left. We go right, we go left, we go right. There is nothing to do, come back. So you got 2. And then we have minus over here, and then we go to the right. We have to go left, go right, nothing to do, come back, then print 3, and finally print plus. Okay, so this is how it works. And do we understand that? I mean, if I give you any such tree, would you be able to write an expression like this? Okay. This is what we call the postfix expression. Okay. So let me write it in one line, because I mean they're all in messed up directions. 2, 3, 5, multiplication 2, division plus 1 plus 2 minus 3 plus. Okay. So what we started off with. It's written up there. Okay, let me copy things over. So this is the original expression. And we ended up with this one. This is what we call infix expression. This is what we humans understand, and this is what the machine understands. Why, you may ask? Because this is easier to process. If you're given an expression in this format, this is really very easy to evaluate. And let me just show you how this is done. See, what we're going to use is a data structure called stack. So some of you may be familiar with the term, some of you may not be familiar with the term. It's a very easy concept. You just imagine this as a tube, and let's say that this tube has one end closed, and we're going to push things out in this way. So let's say I put in some numbers, some random numbers, just to give you an idea. So 10, let's say I put in 5 over here, I put in 3 next. Okay, if I have them, and you can only pick one number out, then the number that you can pick is going to be 3 because the other end is closed. Okay, let me give you another example for those of you who haven't seen stack. I mean, if you're shifting a lot of books from one place to another, you have a small box where you put all your books. You cannot see all the books, you can only see the top one, right? So that's what that stack is like. And you're going to take it out, the top one. If you're going to do dishes, if you're going to wash these dishes, I don't know if you do, well, I had to do that for myself, not for anyone else. What happens is that there are a pile of dishes and you're too lazy to wash them during the day, so at night you see that there is a whole pile. And the first one you put it into the sink, you don't take it out. You take the top one and you wash that. That's how it is. Right? Otherwise things get really, very difficult to manage. So this is what a stack is, and we got 10, 5, and 3. So if you're going to take one item out, you do this one, then you take this one out, and then finally this one. So given this stack, how can we use this stack to our advantage here? See, we're going to process this from left to right. This entire postfix thing, not this infix, this is difficult. Because this is where we have to find out which one we have to solve first. We find out that we have a multiplication that needs to be taken care of first. If you consider this one instead, there is no decision to take. You just process it from left to right. No searching at all. So the first number we got over here is what? 2, going from left to right. So if you find a number without thinking about anything at all, you just push it into the stack. So we just throw that in 2. What do we get over here? 3. So I'm going to repeat myself. If you find a number in here, the only thing that you do is you push it back here. So again, 3. The next thing we got is another number, so no decision to take. You just push it back. So one after another, we are stacking the numbers up. What do we get then? A multiplication. Now this is not a number, so we cannot put it over here. When you have a multiplication, this multiplication is a binary operator. A binary operator means that it works on 2 operands, 2 numbers, right? So if you get something like this, this is when you have to work. This is when you take this 5 out, you put it here on the right side, and then you also take another one out and put it on the left side. Why do we take 2 things out? Because that's binary. It works on 2 things. So we put 5 on this side, we put 3 on this side. Then what do? You multiply them. What do you get? 15. What do you do with that 15? You put it back into the stack. Can you follow this? We have processed these 4 things at this point. So whenever you get a number, you just push it in. If you get an operator, pull out 2 operands, put the first one on the right side, put the second one on the left side. Do the operation, get the result, push it back. It's a very simple strategy. Okay? So now that we have done with this thing, we get 2 next, which is what? A number again. So you do nothing but to leave it in like this. All right? The next thing you get is what? Division. That's why you have to take this one out, put it on the right side. You take the other one out, which is 15, put it on the left side, and then do the division. So 15 by 2 is how much? 7, and then you put 7 over here. Okay? So this is taken care of. Then what? You get plus. And in order to work with plus, what do? Take this 7 out, put it on the right side, take this 2 out, put it on the left side, and then do a plus. We were processing plus, right? So what's the result there? 9. You put that back in. And after that, what do we get? We get 1. And after that, what do we have? Plus. So that means that you take 1 out, 9 out, do a plus. So we get the result, that's 10, put that in. And after that, what happens? You get 2, so you put 2 in. What's next? Minus, so let me write it over here. You take 2 here, 2 out, 10 on this side. What do we have to do? Minus. So these 2, if you take them out, do the subtraction, you get 8. And after that, you get 3, which is you push here. And finally, you got a plus. So you have to take 3 out, put it on this side, right side, pull out 8, put it on this side. And what do? We do plus. So these 2 are taken out. I can't seem to do. Right, got it now. Okay. So the same result, we could find it out, and it was much easier if we were given this postfix expression to start with. Okay. Just by using a stack like this, we can process it from left to right in one go. There is no going back and forth. If you were using this infix expression, on the other hand, there was always going back and forth. You have to find this thing first, which one's first. Take this one, replace the answer, go back and start again. So that means that we humans learn to do maths in a more complicated way than machines do. Okay. For some weird reason. I mean, if we learn how to write postfix expressions to start with, then life would be much easier. Just go in one direction and that's done. That's what we do to machines, right? We make things easier for them, one way or another. All right, so we're going to use a stack, but for us to use a stack, we really need to write this thing into postfix expression, and that can be done if you can draw that tree, or alternatively, you can actually take this infix expression and convert that into postfix by using stack in a different way. But I'm not going to go into detail about that algorithm. If you want to learn how to convert an infix to postfix, because that's a vital part of this whole thing, because otherwise we can't proceed. That's also done through this stack. So for those of you who are interested to know how to convert from infix to postfix, let me just tell you this, that look for infix to postfix conversion on Wikipedia. There is a very nice illustration that shows you exactly how that's done with a railroad construction. This is called the shunting yard algorithm, based on how the railroad works. Like, I mean, if you want to change a buggy of a train, this is how you do. So I'm not going to go through this algorithm, this shunting yard algorithm. Please go through this if you're interested, or even if you're not interested, you'd have to cover this one way or another in one of your courses, either data structure or discrete math somewhere, or even in your algorithm course, you'd cover this. So yeah, go through that. The reason I'm talking about all these things is to say that solving this simple problem is not so simple at all. To do this simple math, it's not really simple. You can't really do this unless you know that shunting yard algorithm, or the one thing that I covered right now, how to evaluate a postfix expression. If you knew how to deal with these things, then that's fine and dandy. If you don't know how to deal with that, then well, you can't. Okay? So since this is the Java course, not the data structure course or the algorithm course, can't really go into that detail. I mean, obviously I can write these things by myself, and I have done that as a student. You should do that as well, just not maybe over here in Java course. I will keep my life simple to solve really easy stuff. So when you're given an expression like 2 plus 3 into 4, I just said that the answer is going to be 20 because that's easy for me. Why? Because 2 plus 3, as soon as I find the first operation, I'll take care of that, and then I will do the second operation. Okay. If you ask me if I'm not doing the right thing, no, I'm not doing that. But in the basic calculators that we get, this is exactly how that works. Okay. If you get a scientific calculator, yes, you can write a big expression, even with parentheses as well. You can do that very easily, and it evaluates things in the right way. But if you get a basic calculator, which doesn't have all those fancy features, it does the very first operation it gets. Okay. Just to process things in a simple way. They don't have that luxury over there. So whatever I've just gone through is all for nothing at this point, because we're not going to implement that. And they're really useful stuff. It's just that you're going to use them in a different context. For us though, just to solve this thing, let's say I want to evaluate this 2 plus 3, what's the answer? We're going to do it in that way. Whatever value we get first is going to be our first operand. Then comes the operator, then comes the second operand, then comes an equal operation. Let's just think about that. Okay. Let's just say that in our world there is just one operation, that's the plus operation, and we can just add two numbers. Okay. If we can solve that part, we can easily do the other parts, and then we can build upon it. Okay. So, how do the basic calculators work? I mean, this is not a basic calculator. It has all the fancy stuff. Even though you don't see sine cos, you can just change the mode over here to, let's say, advanced mode, and you'll see that it really has a lot of features. Okay, so we're not dealing with a basic calculator, but that's really what I wanted to work with. I think I got a picture somewhere. Yeah. So this is something I want to handle. And over here, if I want to do 2 plus 5, when I press 2, it will show 2 over here. If you press plus, actually it doesn't show plus anywhere. In some calculators, they show the operator. In some ones, the very basic ones, they don't. Okay. But this is not a part of the expression. Compare that with this scenario. If you do something like this, the entire expression is shown right on the display. But in our case, we're only going to use the display to display numbers and nothing else. Is that clear? Okay, so that would mean that as soon as I write 2 and then hit plus, what happens is that the entire display will be freed so that I can enter the second number, which is 3. And after that, when we hit equal, that's when it will calculate the result and display the answer back here. So if you follow the sequence, the things that you see on the display is the first number, then you press a operation, the number goes away, you can type in the second number, you hit equal, the answer goes away, gets replaced by the answer itself. So, excuse me, that's okay with you, living in this basic life. Then we can proceed that the steps to take is that as soon as you see the operator coming in, you're going to save the number, the first number, because if you don't, and if you clear the display field, then the number will be lost. You remember what operation that you're dealing with, so that as soon as you get the second operator, you can carry out the entire operation. Okay. And let us look at the design. We don't have a very important operator. button over here, so let me just put that in. I don't, well, I got the picture. So let me just look at this. Yeah, it's in the right place. So this equal operation, the operator itself, is going to be placed right here. That's the equal. Okay? So what do? We do 2 plus 3 equal, and then we get the answer. Okay? We have already written code for 0, 1, and 2. And just to be consistent with the example, and we have to do it for other ones as well, let us just bring in another action. We'll say handle 3 action. Okay, I'm going to save that. And you know the drill already. We make changes and come back over here, right click and make controller. So that's going to be updated. We have a new thing. Okay, so you can copy paste the code for 2. You can put it down here and change 2 things. Wherever it says 2, just turn it to 3, and it's just going to work. So we know how to get the 2 button to work, how to get the 3 button to work. We just don't know how to get this plus button to work. Okay, so let us write code for handle addition action. And handle equal action. Is this clear? We wrote 2 method names, which we're going to write code for, but that's in NetBeans. As far as the design goes, we just need to write down the names over here, and that's it. Someone else will write code for us. Unfortunately, that's going to be the same person, but if you're working in a software industry, someone will design this thing for you, and someone else will write this code for you, or maybe any of these 2 persons. Okay, so yeah, we're going to add 2 and 3 to get the final result. So tell me, what code should we write for this plus button?
Take the previous string and convert it to integer.
Okay.
And then storing a variable.
Storing in the variable? Yep, that's pretty much it. And how about the equal operation? Print the result of the addition, right? That's what happens with this equal operation, and that's what you should display. So let us try to do this thing. Let's make this controller, and we got placeholders for these 2 things, equal and addition. And before I forget, I need to pass the attendance. Okay, so if it were possible that we have 2 numbers, right? Let's say int num1 equal to 2, int num2 equal to 3, and then we could do the result, int result equal to num1 plus num2, and then put that back onto the text field. We could say display text field dot set text and put the result here. Okay, that's how it works, right? We want to display 5. It's just that this is not working right now because the set text method, it expects that you send a string out. Okay, we cannot put a number into the display field. We can put a string in the display field. So the question is, how can you get a string out of a number? It's easy. You just add nothing, add an empty string to that thing, and it becomes a string. So that's moot point, right? I mean, it's obvious over here. So it works. However, the numbers, they're not always going to be 2 and 3. So like Onyx suggested that we have to remember the first number when we hit the addition thing. And how do we do that? Is we read the number old value like we did before. We read that by saying display text field dot get text. Okay, we get a string out of it, and then we need to convert that to a number. That's the first number. How do we get that? This is the method to call. Integer dot percent is the method to call to convert a string to an integer. Okay. Okay, I want to leave it as a homework. It's a very important one, not for this course, but to understand what goes behind the scene. So write a method that converts a string into an integer. So for example, I give you 126, you convert that to a number 126. Okay, so your method will look like something like this: public int convert to int string input. Okay. I don't intend to explain this thing. This is just left as a hint. Make whatever sense that you can make out of it, or nothing at all. Try to do it by yourself, and let me know if you can't do it by next class. We will talk about this thing. Okay. So somehow, right? That's another magic. Somehow, Java converts a string into integer. Somehow it's done. So we got the first number, right? And we need this number over here. The thing is, you have to look at the scope of this variable. We talked about scope of variable in C programming language and any programming language that you learn. You have to deal with that. See, we know concepts like local variables and global variables, right? This integer number 1, this is a local variable. So it lives and dies right here. Whatever value you have in your int num1 will not be available in anywhere else. Even if you use the same name, that's not the same thing. That's why this thing cannot be local, because another method cannot access this. So what's the solution here? You make it global. You declare it in a different place, somewhere like this. Okay. In true sense, this is not global. It's an instance variable of the class. So now we don't have to worry about this number 1 because that's already saved. See, it works. This number 1 is the same as this number 1. They're colored now, and previously they were not. Okay. Now we need to get number 2, and this is what we can do in the equal method itself. Right, when you click equal, you can read the second number, save it, and then go from there. How do you do that? Pretty much the same thing. So let me steal my own code. This is going to be number 2, but number 2 doesn't exist. How do we get it to exist? The same strategy. You declare that over here we got number 1 and number 2. That's that. The result is computed right here, and we show the result. Let us try this out. First of all, with 2 and 3, well, that didn't work, right? Why not? Well, if I hit equal, I get 25. It's actually adding 2 and 23. Okay, but what we expected is that when we write down 2 and then hit plus, this should actually clear out this thing, which we didn't write. So after this is done, after you save this number into this thing, you should clear this out. Display text field dot clear should clear this out so that we can write the second number. So we have 2 plus, this is gone, then 3, hit equal, we got 5. Okay, if you have 5 here and if you want to add 12 to that, it also works. So it's like we can chain these things. As you get the results, you can combine that for subsequent operations. Is this thing clear? So this is at least working for the addition operation. It's just that we cannot do subtraction right now, because if you have another button over here, like subtraction button, if you have a subtraction button somewhere, you have to look at the equal operation. Okay? You have to look at this equal operation because it's always going to add things. This is how it's written. It's always doing the addition. So somehow we need to keep track. Are we doing the addition or are we doing the subtraction? We need to remember that somehow. And that's easy to do if when you're here, you need to remember that the operation that we are dealing with, let's say that we have something like a operation, okay? When you're here in the addition method, you can remember that the operation that we're handling is actually addition. And the method that's supposed to deal with subtraction, it would say operation is equal to subtraction. So if that's the case, then this is easy to handle. We don't know what the result is, but we can say if operation dot equals. I mean, here's a very naive mistake and a very common one. People tend to write this way. If operation equal addition, result will be this. If operation equal subtraction, result will be something else. Well, Java won't allow you to print garbage values, so you have to give it a default value. That's what it is complaining about. But this is wrong, okay? Let me write this out. I will leave it as a comment. Do not use equal operation to compare two strings. You do that to compare two numbers, that's fine. To compare two integers, that's fine. Not even doubles, you shouldn't compare that. But that's a different story. You do string comparison in this way. Please remember this. Okay, so if the operation is equal addition, then you handle this. If the operation is equal to subtraction, then you change this symbol to subtraction. If it's multiplication, just change that. So if I leave it as a homework, it's really a no-brainer. I mean, just add a few buttons for all the operations. You add a few more lines of code. If the operation equals addition, do this. If the operation is equal subtraction, do that. Okay. So what I'm expecting is finish up this calculation by yourself. Shouldn't be too difficult. I will upload this code, but please get this thing done. Let me leave it as homework. Add the other operators. And write code for them. All right. So you'd have a bunch more operations over here for subtraction, multiplication, and division, and then you do the rest over here. Okay. So you do that yourself at home, and I will also do that at home because it's really not going to be too difficult. Then we can talk about the more fun stuff. That's like this one. Okay. This one's more of a challenge. This one is not really. Any question about any of these things? Okay. So in next class, hopefully, we can cover file input and output.